On the sea, under it, and in the air, the navies of today represent the pinnacle of innovation. Or do they? Ancient civilizations may have demonstrated similar triumphs thousands of years ago. Buried in arcane texts are hints of lost technologies. Whitewater rafts centuries before Christ. Battleships powered by a motor that used hay for fuel. Underwater giant mousetraps designed to snare an entire ship. A vessel built solely for the strangest assassination in history. And a weapon of mass destruction that came from the sea. This is the untold story of impossible naval engineering. Fires and explosions strike fear into all of us.
Fire is one of those brilliant weapons that scares the living daylights out of everybody, amateurs and professionals alike. It's an absolutely primeval human emotion.
And in the ancient world, naval commanders used this terror as their primary tactic. Fire ships, laced with chemical combustibles, were the precursors of the modern car bomb. They were rammed into enemy targets. In the 4th century BC, something happened in the Mediterranean Sea that is still not entirely understood. One of the strangest sieges in history ended with an explosion that emanated from the sea. In 332 BC, the island of Tyre in the Mediterranean found itself in the crossfire of a war between the Macedonians and the Persians, the superpowers of their day. The Macedonians were led by the greatest general of the ancient world and perhaps of all time, Alexander the Great.
When Alexander the Great invaded the Near East, he quickly realized that the Phoenicians, who were allies of the Persians, had command of the sea. And the only way he could break that command of the sea was to take out their bases. So he goes for Tyre, which is the great naval base of the Phoenicians.
Tyre is an island half a mile offshore, surrounded by water 30 foot deep.
He has no fleet when the siege starts. What he does is he decides to construct a huge causeway to reach out from the mainland to take the city of Tyre.
The causeway, or mole, is considered to be one of the most audacious engineering feats ever attempted in the history of warfare. Alexander's men began to build a platform made of stone boulders on top of wooden supports, all the way out to the island.
The main danger that the causeway poses to the Phoenicians are the big siege towers on the end of it. The Phoenicians have to destroy these.
Alexander started to drag his enormously heavy siege machines across the causeway. Therefore, when it reached as far as the island, he would be ready to attack immediately.
And the Phoenicians think, if they get here, it's all over. We can't fight the Macedonians in a battle, so they develop a chemical weapons special.
The Phoenicians constructed a vessel laden with brush and dry wood. Above this highly combustible material, they mounted cauldrons filled with a mysterious incendiary mixture. They intended to tow the weapon using 2 smaller vessels and rammed the death ship into the mole, so setting off a terrifying firebomb. The question the archaeologists are now asking is what was in those cauldrons that produced the 500-foot wide firestorm. A leading experimental archaeologist, John Naylor, is investigating the chemicals that the citizens of Tyre could have deployed.
This fire ship, instead of just trying to destroy wooden ships, had to try and destroy a fortification that was being built. That meant that it had to be far more intense and far more powerful.
The engineers fitted out a large transport ship with 2 masts from which they suspended the cauldrons.
As with all ancient references, they're very ambiguous about what the actual contents of this magical mixture might be. What we've basically got there are 3 forms of natural lipids, natural fats. Fats are the energy store of the body anyway, so that's what they are. They're stored energy. We want to release that energy as fire.
John has taken into account what substances would have been available to an island city under siege. We know from contemporary records that beeswax, olive oil, and animal fat were all commonplace in cities of the time. Unmixed and cold, they're innocuous. But when mixed and heated, natural fats in the substances become highly combustible.
So we're experimenting with a mixture of the animal fat, the olive oil, and the beeswax to try and come up with this perfect flammable mixture.
To release the stored energy, the accelerants need to be heated to a temperature of about 400 degrees Fahrenheit in order to reach their chemical flash point.
The flash point is where the chemical, your accelerant, is heated to a point where half a degree over that, it will actually burst into flames. All it needs is one spark past that combustion point, and boom, you've got this explosion of fire, this fireball that sweeps through, destroying everything in its path.
To ensure an instant inferno, the Tyrians had to bring the accelerants as close to flashpoint as possible.
This is getting more than a little bit dangerous. We've got a tiny pilot light burning in the hold of the ship, the cordon of accelerant above it's steaming away nicely. Now that is amazingly effective.
Incredibly, using only products found in any corner grocery shop, John has discovered a potent mix of incendiary accelerants that the Tyrians potentially used on their fire ship.
We've got this. Alexander's men have got to try and put it out. Nearly lost my eyebrows in the process. The whole thing. The harder you try and put it out, the more it burns. And if you try and beat it out, you're just going to get covered in accelerant. That's why the stories tell us that Alexander's men jumped into the sea to try and avoid the flames. That's one scary firebomb. Deadly.
Armed with the results from his successful experiment, John has joined model maker Richard Windley.
Hi, Richard.
Hi, John. Hi.
I've been experimenting, and I think I've come up with the right chemical concoction for the ship. But how's your mechanism going to work?
Basically, we've got the two cauldrons, which is going to hold your concoction. And these are pivoted arms, and we've got like a trip system here. So this is the front, obviously. When these hit the target, these simply knock backwards, knock these two support rods off. That will fall backwards, that will drop.
And catches fire, and we've got an explosion of flame. I think we should give it a try.
Right. We will. We'll get it on the water and see what happens.
The team's objective is to incinerate a wooden palisade at the far end of the lake. In their attempt to recreate the conditions on the fire ship of Tyre, Richard has lit the blue touch paper of the vessel loaded with John's chemical accelerants. As the ship approaches the palisade, the heat from the pilot flame has already driven the mixture in the first pot past its flash point.
Now that would have been terrifying coming towards the mole.
But will John's grocer's shop mixture cause an explosion on impact?
That first impact where we got basically teacups full of that chemical falling into a burning boat, it exploded across the water and onto the water. The water itself seemed to be burning. Imagine Alexander's men leaping off the mole, trying to get into the sea to save their lives, but the sea's on fire. They don't stand a chance.
If we think of cauldrons holding 10, 20, 30, 40 gallons of this stuff, the effect must have been absolutely devastating.
Once they had got the mixture of accelerants right, delivery of the firebomb relied on nothing more than a favorable wind and courageous Marines to haul the ship to its target.
The ship works perfectly. It rams into the mole, the causeway, the inflammable material tips down, the towers are burned.
The devastating effect of the fire ship would have been similar to the tanker conflagrations we're familiar with today. Propelled by wind and because of oil's low flash point, raging chemical fires can still cause severe casualties in the 21st century. Ultimately, however, the Tyrians' ingenious attempt to repel Alexander was still not sufficient to defeat the greatest general of the ancient world.
Probably the turning point of the siege of Tyre is when the kings of Cyprus send their fleets to join Alexander. Once he has naval superiority, Tyre is essentially doomed.
But sometimes the target of a naval death machine was not an army or a siege tower. There is evidence of a bizarre attempt to use a ship to perform an assassination on the last person you'd think anyone would want to murder. The vessel was the brainchild of Rome's youngest ever emperor.
The Emperor Nero was a very bad man. He was almost certainly insane, and he was insane enough to think that he was a great theatrical performer.
Nero ruled Rome at the height of its power in 54 AD, when the empire stretched from the Middle East to Western Europe across 4,000 miles. It was an unprecedented amount of power to bestow on someone so young and so volatile.
Nero goes down in later classical history as one of the all-time bad emperors. He's a bad, psychopathic, Oedipal madman.
Nero's brutality even extended to his own family. In 59 AD, after becoming angry with his mother Agrippina, the emperor decided to kill her.
Nero can't straightforwardly have his mother executed. She's extremely popular. So what he has to do is arrange an accident.
To do the deed, Nero enlisted the help of a character who was clearly as unhinged as himself.
Anicetus, who was a friend of Nero's who he'd grown up with, was actually in charge of one of the Roman fleets. And it was him that came up with this really bizarre idea. It sounds so far-fetched, it's almost unbelievable, to entice Agrippina onto a ship that had been specially prepared, and hopefully Agrippina and any of her entourage would be killed.
The self-sinking ship would become infamously named Nero's Death Yacht. For almost 2,000 years, the question has been asked, how did it work? According to the illustrious Roman writer Suetonius, a signal having been given, a crew member pulled a cord attached to the canopy adjacent to the cabin. The entire roof of the cabin crashed onto the deck with enough force to crush to death anyone underneath. The exact mechanism of how this was achieved remains an enigma, but ancient technology specialist Richard Windley has a theory as to how it could have worked, using well-understood engineering principles of the time.
What we can see is the false ceiling, which is this big flat area here. Each of these is simply notched, and there's a lever latch which locates into each of the notches. So this whole ceiling is supported by these 4 lever latches. The rope from each of the 4 latches are connected together, so we've got one rope coming out. All this needs is one really good tug, and this whole ceiling will then collapse, like so.
Agrippina was lured onto the ship under the pretext of an elegant supper cruise down the coast from the town of Baia on the west coast of Italy. As she and her 2 servants relaxed in the cabin, the signal was given. Tons of lead thrust the roof to the floor, killing one of the servants instantly. But the wicked scheme had a flaw. Agrippina was lying on the solid couch in the cabin, which protected her from the falling ceiling. Pandemonium broke out. Many of the party fell overboard in the chaos. The boat maneuvered through the darkness, hunting for Agrippina. Unaware of the shambolic assassination attempt, one of the guests pretended to be the queen in the hope of a quicker rescue.
A friend of hers, who's swimming nearby, calls out, "I am Agrippina," and is promptly clubbed to death with an oar.
It appears that Agrippina immediately realized what had happened.
Agrippina very wisely keeps quiet. She's got a shoulder injury, but she swims until she finds a fishing boat, which takes her ashore.
To finally accomplish the murder of his mother, Nero resorted to a more traditional Roman method.
He has to resort to what one has to say is quite the easiest way of bumping anybody off in the ancient world, which is to stick a knife in them.
Despite the dastardly ingenuity of Nero's attempt to assassinate his mother at sea, the death yacht was simply too elaborate to succeed. Indeed, many ancient naval inventions overstretched themselves. Others, though, might just have worked. Lurking beneath the surface of those waters was a trap no sailor, past or present, would ever want to spring. Today's superpowers wage a constant battle to protect their ports from enemy attacks and smugglers. From New York to Hong Kong, each major port employs high-tech security measures to ensure the safety of its citizens and the protection of its lucrative cargo and trade routes. The ancient world was no different. Ports and port cities were the commercial hubs of all ancient and medieval states.
These are the front doors of the states of this period. They are absolutely critical to all the major empires, right the way through to the modern world.
but their very importance made them prime targets for enemy invasions or attack.
Ports are very hard to defend. Fleets can appear out of nowhere. In the morning mist, an enemy fleet can arrive.
Italy. In the 15th century, with the birth of the Renaissance, port cities all around the peninsula were enjoying an explosion of wealth and new opportunities. This made them inviting targets for pirates on the hunt for slaves and booty.
There is no at-sea police force. There is no established navy. There is no body out there to protect you from hostile threat. And the Mediterranean is at a cultural crossroads. All along the southern shore of the Mediterranean are city-states, Muslim city-states, who live on corsairing, state-sponsored piracy. Their job is to make money by taking swag and slaves and taking them back and selling them in the markets of Algiers, Tunis, Tripoli.
But in addition to gold, the pirates sought a more sinister prize.
One of the targets thereafter are the younger generation. Children are very attractive. You can bring them up in a different faith, you can train them up in different skills. If they're pretty or handsome, you can sell them for a high price.
Port cities were desperate to develop naval defense systems to protect their wealth and also their children. The engineer who could offer a workable solution would become an overnight celebrity.
Engineers are immensely important. You looked, if possible, to use local engineers because they're more likely to be loyal. But the main military engineers were keenly sought after and paid good money.
But it was complicated. The defense system had to protect the port from enemies while still allowing friendly boats in and out. The free passage of trade was essential to the economic well-being of the city.
They had to find an area denial system that would keep the bad guys out, that offered them the option of doing that with the existing materials.
Contained within 15th century Italian manuscripts, the Ancient Discoveries team has uncovered evidence of a set of bizarre submarine mechanical devices. These were machines that were designed in response to raids on the coastline from hostile vessels. The most radical was known as the keel breaker, a hull-piercing device designed to protect the shallow lagoons and marshes against pirate attack.
It's a system for use in fairly shallow water. It's not a deep water system. It's to stop light draft pirate raiders coming in. It's not to stop heavy warships. This is about closing off low-lying, relatively shallow areas of water.
The drawings are attributed to an obscure artist and engineer who worked in the city-state of Siena in the 15th century. His name was Taccola.
We know that he did administration for Siena. We know that he did a bit of sculpture, but we don't really know where to locate him in professional terms. But he clearly was highly prized in Siena and was very inventive, did these two big manuscripts, really showing what he could do.
The concept of Taccola's keel breaker was that when the trigger mechanism was tripped by the hull of an enemy ship, a counterweight was released downward. This released a claw that extended upwards, piercing or tearing the hull of the vessel. The problem is we don't know if the keel breaker was just an idea on paper or whether it was actually deployed in anger. Ancient Discoveries team member and leading ancient model maker Richard Windley is recreating a working model. If it succeeds, it suggests the design might have seen action. Basing his model on the actual sketches of Taccola, drawn over 500 years ago, Richard is constructing the component elements of this hitherto untested maritime area denial weapon.
One of the problems with any kind of ancient reconstruction, whether it's 15th century as this piece or earlier, is that if we've got no archaeological evidence of these things, so the difficulty really is trying to work out exactly what sort of materials, what techniques they would have used to construct them. So it's a question of thinking about the materials they had to hand, the kind of techniques that they were familiar with and that were commonly using.
He has brought his machine to the underwater stage at Pinewood Studios, where hundreds of feature films have been made, to perform a series of tests.
Really, there's no reason to suppose that in Taccola's day it wouldn't have been done in a similar fashion, i.e. the parts produced in a workshop somewhere locally and then all the parts transported to the lake shore, assembled and then towed out onto the lake and sank.
Richard has used a combination of sawn and raw timber in his reconstruction of the machine. Where Takala would have probably used iron, he has used mild steel to make the major metal components.
This is all the components of the keel breaker assembled into its final version. And as you can see, we've got a fairly heavy wooden box frame to sink it to the bottom of the lagoon into its final working position. The main working part of it is this arm, which is very similar in effect to a trebuchet. We've got a long arm, a big heavy weight at one end, and the actual projectile, which in this case is a big steel kind of arrowhead. This arm, under the influence of the gravitational pull of this big heavy weight, will flip over at quite high speed. And the idea is obviously that the point would impact on the enemy vessel.
So this is the keel breaking replica?
Yes, that's right. That's right.
Richard is joined by naval historian Professor Andrew Lambert, who has studied the sketches of the machine in detail, but he's never actually seen one in the flesh. Both men are sailing in uncharted waters. Neither knows how the device will actually behave off the page and in the real world.
Because if you can see it all, it's not much of a surprise.
Well, that's right.
The first question is to see whether the machine's basic principles are sound.
Andrew is going to pull the cord to release the trigger of the device. I'm going to stand just to the side so I can get some idea of how fast and how far the projectile is travelling. OK. Count down. 3, 2, 1, pull. Well, that's looking fairly violent, and I think anything that got in the way of that would certainly take some damage. Whether the spike would impale or go clean through a hole, I suppose it would depend on how solidly the boat was built, but there's certainly plenty of power there in the air.
The keel breaker appears to be the perfect trap, but was it? There was something else lurking beneath the water, something that might stop this macabre machine dead in its tracks. Of all the naval innovations developed in the ancient world, few seem more unlikely to work than this one, a device called the keel breaker, a truly terrifying example of coastal defense. Could it sink a ship and eviscerate the sailors on board?
I think the problem is going to be the depth of water. I think the water pressure down there will slow the movement of the arm, it will slow the descent of the weight, and the whole thing will be significantly less dynamic than it was in air. And it's a question of whether it achieves the kind of effect that it needs, which is enough momentum to penetrate into wood and to drive that spike into the side of a vessel.
Because of the wood's natural buoyancy, the underwater team is fixing weights to the bottom of Richard's keel breaker. These will ensure that the machine stays on the platform that is set 9 feet under the surface of the water. The weights must provide a downward force greater than the upward force of the buoyancy of the wood. But buoyancy is not the only problem created by the intrinsic properties of water.
The latch is in position, so the device is on now, and this is the state that it would be in on the lake bed.
Water is roughly 1,000 times denser than air. This means that for the keel breaker's 40-pound iron claw to overcome the water's resistance, the counterweighted mechanism will have to produce 10 times more energy in order for it to work efficiently.
Clear. 3, 2, 1.
As we thought, the sort of hydrodynamic nature of the action is slowing down the weight, it's slowing down the arm.
The arm is far less destructive underwater than it is on land. But the power generated by the counterweighted mechanism may yet be sufficient to pierce the hull of a ship. Using a 4-inch thick section of wood to represent a pirate vessel's hull, the team will put the theory to the test.
What we have to hope with this test is that the weapon will have enough energy to secure a lodgement in the side of the ship and to actually pin it. Wooden ships are very difficult to sink anyway, because wood, as we've seen, floats rather well. So pinning it and holding it is actually the quickest way of dealing with it, because then you can do the best thing about wooden ships, which is to kill the crew. Then the ship's yours.
With the mechanism set, the moment of truth has arrived for the team's keel breaker. Andrew will use ropes to trigger the mechanism from above the water, while Richard analyzes its performance from the underwater viewing window.
3, 2, 1, release.
be honest, that didn't look overly powerful. It's hard to tell just from here whether we've impaled the hull or not, but we certainly didn't burst through the hull, which is kind of really what I was hoping it was going to do. It cast doubts on the viability of the machine.
The results from the final test have proved that while the keel breaker could have been deployed to trap the enemy vessel, Richard's machine was defeated by the laws of hydrodynamics.
This was a really interesting idea based on a proven land technology, the trebuchet. Take it to sea, and the fact that it's under the water transforms its performance and means that it doesn't work anywhere near as well as you want it to.
The counterweighted mechanism simply does not have enough power to overcome the water's resistance.
The most important thing it tells us about technology is that it's not a straightforward linear process. Weapons technology didn't start with sticks and stones and go all the way through to the modern world without people making endless mistakes. There is no direct line.
Ultimately, the reason why Tackler's design never took off is that the investment in manufacturing such a machine would not have been repaid by success in combat.
You look for another technology, you invest your money in something else, and ultimately that something else is going to be cannon.
Engineers like Tackler were not only interested in stopping ships, they were also interested in making them go. The science of moving an object forward is known as propulsion. Propulsion has allowed man to conquer the oceans, the skies, and ultimately, space.
Propulsion in its simplest terms is the thrust that a vehicle gets by moving a fluid or a gas. So in the sense of a helicopter, you have the air being forced by the blades of the helicopter at the ground. In a ship, you have the water being pushed out the back either by a propeller or by a paddle or by a jet. And in an airliner, you have the air being pushed out the back of a jet engine, and that's giving you thrust and is moving the vehicle forward through the air or through the liquid.
But in the ancient world, inventors were trying to develop ideas that got something for nothing. For example, a vehicle that could run without petrol and a ship that needed no sails. The adventurous medieval engineer Tackler proposed a boat that required no power at all, other than that of the current of the water flowing under it. Biomimetic engineer Dr. William McGill is investigating the mechanical principles of the design in his laboratory in Britain.
We looked at Tackler's designs and at his drawings, and we do the math, work out the algebra of what the forces ought to be on it. And then the next stage is to go and draw it in a CAD package, in an engineering package. And from this, once we have all the dimensions worked out, we can then actually just hit print and run it through a rapid prototype machine. And, well, the plastic parts in this are what comes out of the rapid prototype machine.
In Tackler's time, there was no automated way to travel upstream in a boat. Using a water tunnel to recreate the upriver conditions, Dr. McGill will test the gearing of the boat.
The rope is tied to the bridge at the end, and he has the rope then tied around the drive shaft of the spinning wheels. And then as the crank turns due to the flow of the river, the rope is then tied around that capstan, and that's what then brings the boat forward through the water.
The experiment has discovered that although Tackler's boat would not have broken any water speed records, it certainly would have functioned in an upstream environment.
The faster the stream will flow, the more force you get in the paddle wheels, which will enable you to pull yourself up the river more quickly. And so provided it could be geared to work, it would work in most situations.
Perhaps the strangest example of naval propulsion is found in an enigmatic text known as De Rebus Bellicis, the authorship of which is still uncertain. The evidence here suggests that Roman engineers employed a motor that used not horsepower, but bull power.
In an ancient pamphlet, there's a wonderful description of an oxen-powered Roman warship. It's from the later 4th century AD.
The unidentified author of the manuscript makes the first known suggestion that a ship can be propelled with neither sails nor oars. It's a staggering proposal, If his theory is sound, it means that self-propelled ships are more than 1,000 years older than previously thought. The manuscript describes oxen aboard the warship, tethered to and walking in circles around a pole. This turns shafts connected to paddle wheels on the outer walls of the hull. From the blueprint, the deck of the boat is estimated to be about 15 feet wide. The drag from a 15 feet wide boat using 6 oxen as its power of source indicates that the boat would have a maximum speed of only 1 knot. Many researchers remain skeptical as to how effective oxen power was. Dr. Geraint Owen, one of the world's foremost experts in mechanical engineering, is looking at the design.
Whilst this may not have been a great sort of military success in period, the application to the ferry-type environment has some validity, and so it shouldn't be dismissed sort of as being a completely useless invention.
19th century accounts tell us that horse-powered ferries could carry passengers across the East River in New York in under 10 minutes. The reason why this propulsion method disappeared somewhere between ancient times and 19th century New York remains a mystery. Some people have argued that in a world where slaves pulling oars was cheap, the complicated mechanics of the oxen-powered boat was simply not cost-effective.
On the deck of the boat, we have a sort of capstan-type arrangement where the oxen would walk in a circle, a pair of oxen, and they would have to drive some sort of gearing arrangement underneath the deck of the ship, in the hold, as it were.
It's known that the ancient engineers were able to design geared systems using simple peg-drive bevels, which are much the same as the wheel and pinions in modern cars.
Modern equipment, we talk in tens and hundreds of horsepower. This, we're talking with 3 pairs of oxen, we might just get to 2 horsepower. And so if you think of an ox produces perhaps half a horsepower, I can now go to a DIY store and buy a cordless portable drill that is of that sort of power output. An ox will only produce enough power to light up 3 light bulbs.
The investigation into the oxen-powered warship has demonstrated that the anonymous inventor was very forward-thinking. He was able to convert the energy that was produced by the oxen into a 90-degree gearing system, a principle that underpins most modern engineering. It was only that the energy density of the oxen was not sufficient to make the warship as potent as the inventor had wished.
Overall, it's a sound design in a paddle-powered boat. It's just that it's way ahead of its time because the steam engine hadn't been invented and it had to use animal power instead.
For millennia, the planet's vast networks of rivers and oceans have been used to transport billions of tons of cargo. Even today, in a world of aviation and railways, riverine transportation is still vital for global logistics, with rivers handling around 1 billion tons of cargo every year.
In the ancient world, it was just the same, only they didn't have roads and they didn't have railways, so the only economical system for moving heavy amounts of material was water transport, rivers and the sea.
From the Nile in Egypt to the Yellow River in China and the Tigris and Euphrates in Mesopotamia, rivers in the ancient world were the motorways of their day.
This is how the ancient world moved goods, supplies, food, people. It's how it moved supplies for war, everything.
The 1,150-mile-long river Tigris that rises in the mountains of Turkey and comes out in the Persian Gulf was one of the most dangerous trade routes in the ancient world and was known as the Tiger because of its ferocity.
The Tigris, particularly when it's in flood, is a very dangerous, ferocious force.
The Tigris had whitewater rapids, similar to these. Today we conquer stretches of water like this with heavy inflatable rafts. But in an age before modern synthetics, how did the people of the Near East subdue such treacherous waters? At the British Museum, Dr. Paul Collins is examining evidence that the Assyrians were able to travel the river as far back as the 7th century BC.
Well, these are the wall reliefs from the Assyrian capital of Nineveh. They date to around 700 BC, and they're great slabs of carved gypsum which once lined the major rooms of this royal palace. Most of them showed scenes of battle, but these particular reliefs show the movement of goods and materials.
With the river as the main means of transport, everything society needed was transported along its currents: grain, livestock, people, even soldiers on their way to the battlefield. Floating downstream with the speed of the current behind them, the rafts could travel up to 6 miles per hour according to the weather and seasons. These may have been history's first whitewater rafts, a dangerous way to move goods, but fast.
If you wanted to move materials, for example, between the site of Mosul in northern Iraq and the site of the capital at Baghdad, it's about 200 miles. So by foot or donkey caravan, it's a considerable distance to travel. And by boat, even if you were moving short distances on small craft, it's a much more effective and convenient way of travel.
Instead of heavy rubber, the ancients used inflated animal skins to make their vessels buoyant.
An inflatable craft with water buoyancy based on air-filled vessels is ideal, because if you hit the side, you burst the odd animal skin, you get by. That night, you patch them up, pump some more up, and you're away again in the morning.
The Ancient Discoveries team has a challenge. It's brought together a panel of experts who will attempt to construct the world's first whitewater raft using only natural materials. The craft will be tested on a river in Wales. Will the ancient technology work? Will the team even be able to get their vessel to float at all? Using information from 2,700-year-old relief sculptures, the Ancient Discoveries team is attempting to recreate a whitewater raft built to crest the dangerous rapids of the River Tigris 2,500 years before the invention of synthetic materials. For the first time in thousands of years, the team will test ancient Assyrian technology on natural whitewater rapids. The raft was an integral part of the Assyrian transport network and delivered everything from passengers to 10-ton blocks of stone.
The main thing with these river rafts is to have a wide, stable but shallow vessel that will carry people and cargo when it's big enough, without taking up too much water, and a bit of flexibility too, presumably so it can ride over the odd boulder and shallow patch.
Damien Goodburn is one of the few archaeologists in the world keeping alive historical boat-building techniques. The old accounts reveal that the wooden frame was simple in its construction technique and required only small trees to make it. This was in contrast to other boats of the time that required very large trees for their construction. Damien is using soft green timber and is fastening the wooden poles together with vegetable twine. Reed mats are placed on top to form the base upon which the cargo will sit.
We're in a slightly different environment. There are small differences between our raft and the sort of rafts they used in the ancient Assyrian world. The basic challenges are going to be very similar.
Professional hide worker Peter Faulkner is investigating the buoyant properties of materials found in nature.
This is how it starts. I go to the butcher's and I go through the hides, find one which is the right size, hasn't got any holes in it. This came off the beast a couple of days ago. It hasn't been fleshed, that's got to be done, but it has been washed on a power hose.
The insertion of a camera inside the hide shows light coming through, which reveals how thin and lightweight the hides are. This is vital, as the flotation devices must be as light as possible, as well as strong and watertight. Using clues from the wall reliefs, Peter is employing ancestral techniques to stitch the hides together.
Right, this is the last one.
The dried hides are tough and rigid. They retain their shape much like a plastic buoy, so they don't need to be pumped up like an inflatable mattress. With the structure and the flotation devices complete, there remains only one thing to do: take the craft to the water. The River Wye flows through the Black Mountains of South Wales. It boasts some of the most treacherous rapids in Britain. The stretch of river selected for the test is exactly comparable to the stretches of the Tigris the Assyrian boatmen would have had to confront.
I honestly believe it won't make the first rapid. I can see them bladders either coming off or bursting before we hit the big rapids.
It's a bit of a shock, really, to see this raft. If you add in the consideration that the raft's 2,000 years old and it's been made out of, all natural materials, then that ups the danger factor, I suppose. So, yeah, it's a little bit disconcerting.
The last procedure is to give the hides a final coat of waterproofing substance.
We're melting the lanolin. The lanolin is the most very solid, and that's going to be made into hot liquid form, and then it'll work, and we're going to paint the floats. It'll obviously make them waterproof, but it'll also give a bit of slip in the water, and also if you do hit a rock, it may just help that little bit.
Lanolin is a mixture of cholesterol and the esters of fatty acids. It's produced by boiling the wool of animals, such as sheep. When applied to the animal hides, it creates a waterproof seal. The team can now make the final assembly. 2,500 years after it was first used, the team have created an Assyrian raft in exactly the same way the ancients did.
It's going to be extremely interesting to see how this ancient technology copes with a relatively rapid river. It's a challenge to the skill of the rafters now. We've done our bit, and now it's up to the people who know the river and know how to handle a raft.
The ancient discovery's Assyrian raft will have to float 650 pounds of the crew's weight with only the inflated hides of 4 bovine animals.
I think it's floating, and that's a good start. It's floating quite high. It's raining, the river's going to come up and make it even more exciting.
Let's take the weight off and give it a go then.
The most dangerous part of the course is known locally as the hellhole, and it's where the rafting experts believe the raft will probably disintegrate. The 2-mile adventure begins in relatively calm water.
It's been kids this angle, boys, and we're on a good ferry angle, heading straight for where we want to be.
Rafting specialist Dave Proctor uses his 25 years of experience to expertly navigate the most hazardous parts of the 50-foot wide river.
Yeah, keep it going.
The first part of the course having been completed, the team begins the descent to the hellhole. A safety team has been deployed in case the raft breaks up. Damien and the others wait apprehensively at the finishing point of the test course. The safety boat emerges, but there's no sign of our intrepid rafters. Despite the apprehensions of the team of experts, the old technology has survived the course with its structure and crew intact.
We've proved that the basic system of skin float rafts works, even in less than perfect sort of Near Eastern conditions. It's a real challenge for the raft people here. They know what they're doing.
Well, against all the odds, here we are. Very exciting run. A little bit floppy towards the end, but we got from the start to the finish. What more can we ask?
Rafts almost identical to this one rode the rapids down the Tigris thousands of years ago. Some of them carried up to 40 tons of stone or whole herds of livestock.
We certainly didn't nurse it down the river. We took a few hard knocks and we hit a few rocks, but I think the construction method gave it a little bit of flex, and that helped. Without a doubt, I think you could say that the 2,000-year-old technology is definitely a success today.
Using just 4 animal hides and timber, the test has proved that the ancient technology would have been more than capable of tackling the rapids of the River Tigris 2,500 years ago. Some naval technologies shaped history and so the world we live in today. Others pushed the envelope of invention too far, and whilst they continue to amaze us as ingenious ideas, they probably didn't work.
Ancient engineering would have been driven in some ways by the same as modern engineering, the requirement of advancing technology to make more efficient